Welcome, engineering students! Let's jump right into today's explainer, based on a formal lecture prepared by Dr. Nima Mahadian. We're going to maintain a strict focus on industrial PID controllers. Specifically, we're examining their architectures, practical applications, and, crucially, their fundamental limitations in the field.
Here's a quick look at our syllabus. We're progressing logically from the foundations of PID control and PI control architecture right through integrating derivative action, hardware realities and filtering, and finally, boundaries, practical deployment, and our summary.
All right, let's start with Section 1, Foundations of PID Control Core Theory. Let's unpack the complete mathematical flow of a closed-loop industrial PID controller. It all begins on the left with our reference set point, R of t. Now, this is compared against our feedback to generate the resulting error signal, E of t, which feeds directly into the PID block. The controller processes that error to produce its output, U of t. That control signal is what actually drives the plant or process, resulting in our final process output, Y of t. And crucially, the sensor or measurement block closes this whole loop by feeding Y of t right back to be compared against our initial reference, R of t. It's an elegant, continuous loop.
What's really fascinating here is how the three pillars of dynamic control are broken down by their specific temporal roles. First up, we have proportional, or P, which represents the present. It reacts proportionally to the current error state. Next is integral, or I, representing the past, accumulating historical error over time to eliminate steady-state offset. And finally, derivative, or D, representing the future. It actually predicts error trends based on the current rate of change to stabilize the system. But here's the critical engineering insight you need to remember. While proportional and integral actions can absolutely operate independently, derivative action cannot exist alone. Standard industrial configurations always combine these into PD or PID structures.
Moving on to Section 2, PI Control Architecture, the true industrial workhorse. It's honestly easy to see why PI control holds that title of industrial workhorse. It is the dominant architecture, making up between 60 to 70% of all industrial PID structures. Why does it win out so often? Well, it strikes the perfect balance. You get structural simplicity paired with high operational accuracy, successfully eliminating steady-state error entirely without having to introduce the complexities of derivative action. So, let's look at the mathematics behind this. The equation for automating the manual bias, known as reset control, goes exactly like this. U of t equals k times the quantity, E of t, plus 1 over t sub I times the integral of E of tau d tau. Let's break that down. K is the proportional gain, driving the immediate response to current error. T sub I is the integral time constant, which determines exactly how aggressively past errors are accumulated. And K sub I, which is K divided by T sub I, is known industrially as the reset mode. Historically, operators actually had to add a manual bias, or reset, to remove steady-state error. The integral component mathematically automates this tedious task, forcing the final error exactly to zero.
However, we have to be realistic about the inherent limitations of the PI architecture. The first big limitation is speed. Because the integral action relies heavily on accumulating historical data, PI control doesn't significantly improve the overall speed of the system response. You end up with a slow response curve to reach the target. Limitation number 2? It is completely blind to the future. The PI structure is purely reactive. It simply cannot anticipate or predict near-future errors that are already developing within the system dynamics.
That brings us perfectly to Section 3, Integrating Derivative Action, Anticipating Error. To solve that blindness, we introduce prediction via the PD architecture. By analyzing the rate of change of the error signal, the derivative, or D element, predicts exactly where the error is heading. It is literally anticipating error. The system impact here is immediate. Integrating this into a PD structure improves overall control speed and dramatically enhances system stability. It does this by applying a powerful braking effect right before the target is overshot.
And that brings us to the complete architecture and the true synergy in PID. Let's walk through the full theoretical equation. U of t equals k times E of t plus k sub I times the integral of E of tau d tau plus k sub d times the derivative of E of t with respect to t. This beautifully breaks down into 3 synergistic blocks. Block 1 gives us speed from the proportional term, offering immediate dynamic response to present conditions. Block 2 layers on accuracy from the integral term, eliminating offset by accumulating past discrepancies. And finally, Block 3 ensures stability from the derivative term, which predicts and dampens oscillations by analyzing the trajectory.
Now for Section 4, Hardware Realities and Real-World Filtering.
let's talk about what happens when theory meets physical hardware.
We need to understand a phenomenon called derivative kick. The problem happens when sudden step changes in the set point, or the input, cause massive instantaneous changes in the error signal. Mathematically, the consequence is severe because the derivative of an instantaneous step change is, theoretically, infinite. The real-world hardware impact of this is profound. It sends a massive, rapid shockwave through the control signal, causing extreme system shock and risking severe mechanical damage to physical actuators and system hardware. No one wants that on their factory floor.
Furthermore, we have to contrast our beautiful theoretical clean signal with the noise-ridden reality of industrial environments. The core problem is that the derivative component is inherently hypersensitive to high-frequency variations. Out in the real world, sensors constantly pick up minor electrical or mechanical noise. Left unchecked, the D component will amplify this invisible high-frequency noise into aggressive, erratic control signals. It completely destabilizes the process, turning a smooth, theoretical sine wave into a chaotic, erratic reality.
The practical solution? Derivative filtering. In pure theory, the derivative term is simply S times T sub D, but the reality equation transitions to S times T sub D, which is approximately equal to S times T sub D divided by the quantity 1 plus S times T sub D over N. How it works is quite simple. To eliminate that derivative kick and noise amplification, an extra pole is added to the system. The vital role of the integer n is that it restricts the derivative's gain at high frequencies. This specific mathematical modification is exactly what bridges theory to reality, making the D component genuinely safe for execution in actual microprocessors and physical hardware.
Section 5. Boundaries and Practical Deployment. Let's look at exactly where to use PID. Let's compare deployment strategies to see when you should actually use the derivative. An ideal application is a thermal or inertial system. Systems with high thermal inertia, like industrial furnaces, respond quite slowly. Here, the predictive nature of the derivative is absolutely crucial to break heating early and prevent massive temperature overshoots. Conversely, a poor application involves dead time or delay. Systems characterized by significant transportation delays confuse the derivative action. Applying D here often causes absolute instability. For those scenarios, advanced techniques like Smith predictors are strictly required.
Building on that, there are 3 absolute boundary conditions where standard PID controllers just hit a fundamental operational wall. Path 1 is MIMO systems, meaning multi-input, multi-output processes where variables heavily cross-couple and interfere with each other. Path 2 is nonlinearity. These are highly complex systems with dynamics that shift wildly, requiring continuous and frankly impractical retuning. Path 3 is severe dead time, which are processes where the delay between action and measurement is massively disproportionate to the system's time constant. We also absolutely must highlight a massive blind spot, handling system constraints. The critical issue is that the standard PID algorithm is mathematically blind to physical world limits. The implication of this is critical for safety. If a process variable, like pressure or a chemical concentration, must remain strictly below a defined safety threshold, standard PID cannot inherently enforce this. Therefore, additional safety logic, override controls, or advanced architectures like MPC must be built around the PID just to guarantee safe operation.
And finally, Section 6, Summary and Final Selection. Let's stack these architectures up in a final selection matrix. First, for eliminating offset, P and PD do not, while PI and PID successfully do. For predictive capability, P and PI do not, whereas PD and PID absolutely do. Looking at noise and kick risk, P and PI maintain a low risk, while PD and PID inherently carry a high risk and strictly require a filter. Finally, for industrial popularity, P is niche, PD is rare, PID is specialized, but PI remains the 60 to 70% dominant choice across the board. Which brings us to our conclusion. Despite its vulnerabilities to dead time, noise, and complex nonlinear dynamics, the PID framework, and specifically the PI architecture, remains the undisputed baseline of industrial automation. Its unmatched balance of structural simplicity, reliability, and tunable accuracy makes it the foundational algorithm upon which modern industry runs. So I'll leave you with a provocative academic question to consider. Given its deep integration and unmatched reliability, what future framework could ever completely replace the PI architecture in industrial automation? Thank you all for your focus today.